Okay, so let's start. Something I want to say before we go to the topic. I am an Atlas ambassador. Everybody knows which Atlas. Atlas is a right device that can plug into your network. Never mind if your home network or your office network. If you want to get free one of these to allow you and the rest of the community to do measurements, I have in total 10. I have only 4 here. I will collect the rest of them in my room during lunch. So at the end of the session, I can provide 4, and then I can provide 6 more. It's free. You only commit to really plug it and have a power socket, of course, and RJ45 socket for the Ethernet connectivity, and that's it. After that, you register in the right website, and you can get your own measurements, or you can help the community to do measurements. Okay, so it's really useful to do global measurements across the internet, but also for yourself, not just for the community. You can decide if you want to make this probe public so others can use it, or just for your own use. So no difference. You can just use your own and not make your measurements public. Okay, so there is not a risk of anything that you don't want to disclose to be known by everyone. Okay? So at the end of the session, again, I have 4 of them here, and then I will bring after lunch, in the second part of the session, another 6. Okay, going to our topic. First question, how many of you are ISPs? Everybody? Half, okay. Enterprises? Okay. Maybe education, research? Nobody? Okay, so I have a feeling, more or less. Another question, how many of you have done already some IPv6 deployment, even if it's just a lab? So half, more or less? Okay. Important point here. I am not going to talk about IPv6 basics. So I understand that you have some IPv4 knowledge and some IPv6 knowledge, okay? That's important. Anyway, I think including the time that I have for both sessions, we have some spare time, depending on the pace that we go with the presentation. I am not in a hurry. I am not interested in going through all the slides. I am interested in making sure that you get a good idea about how to deploy IPv6, especially in the access network, in the transition, okay? So that's the key point here. So if you feel I am going too fast, too slow, if you have something that you don't understand, even if it's not in my presentation, at any time, there is another mic here, I can pass to you. We need to use the mic because the session is broadcasted, so the remote people can hear also your questions. So interrupt me at any time with any kind of question you have. If it's something I am going to talk later, I will tell you, wait, it's coming later. But if it's something is not in my talk, I can provide an answer at that time, okay? So let's try to make it very interactive. And if we have enough time at the end, we can see even some specific examples. If you describe a little bit your network, I can probably give you some hints about how to deploy IPv6 in that specific case. Of course, we don't have the time to make a complete analysis, but at least an overall idea. Okay, that's the main point of these 2 sessions. So in the first part of the session, which is from now to before lunch, I'm going to talk a little bit about what is transition and what are the different key, not all of them because there are too many, but the key transition mechanisms, and my view you according to my experience doing deployments. We have done deployments, training, consultancy in about 120 countries already in the world. So we have a little bit of experience. We started in '99 doing IPv6. We participate, we are a small company, we participate in IETF standardization, we do trainings everywhere in English, Spanish, and we do consultancy and deployment of IPv6. So it's a very, let's say, personal view, but based in real experience, not just labs, okay? And of course, we have customers of all kinds. We have customers which are governments, universities, ISPs of different sizes. So I'm using different access technologies, of course. I recall one of the first trainings the first training and consultancy we did in Costa Rica. It was an ISP that had 26 different access technologies. You can get an idea about what a mess to deploy IPv6 over there. Of course, some of those access technologies don't support at all IPv6. It will be so difficult that the only way was doing tunneling. Okay? We will talk during the session about that, and then after lunch, I will try to describe how you can use the knowledge of the first session to deploy IPv6 in broadband networks and cellular networks. And the basic idea is to deploy IPv6 only, not anymore IPv4. Why? Because there is going to be a point, for some people that happened already, where you don't have enough IPv4 addresses to keep deploying IPv4. So we can deploy IPv6 only and still provide IPv4 at the edge as a service. So we call that IPv4 as a service on top of IPv6. Okay, so you don't let your customer to disconnect from the IPv4 network, but in your access network, you just need to support V6. Okay, and it's the customer CPE or the cellular phone, the one that is doing the IPv4 thing. Okay, so that's the description of what we are going through. From those that are ISPs here, how many already have cellular networks? Nobody? One? Okay. Okay, so let's get started. First question here. There is a lot of people that is talking about IPv6 migration. That's wrong, it's broken. There is no such a concept as migration. If you look at the IETF standards, they are all transition mechanisms. You never will see migration mechanism. What is the difference? The difference is that when we started developing IPv6, we had a clear understanding that we cannot get rid of IPv4 overnight. We cannot tell, let's agree on a date and a time, disconnect IPv4 everybody in the world, and in the next minute, enable IPv6. That would be migration. So in some languages, it happens sometimes in English, transition and migration looks like the same, but for example in Spanish it's not. And I think the best way to see that is when you do a migration from Windows 2000, I know it's very old, to Windows 10, okay? You don't keep both operating systems working at the same time. You install the new operating system and you get rid of the old one, okay? That's, in general, not what we are going to do with IPv6, especially in the access networks. For me, access network is both the customer, the LANs in the customer, and the content providers. If you keep IPv4 in some websites, which we know it happens today, you still need some kind of IPv4 support in the LANs of the customers. Okay, you see that? So the way we design it in IETF, the transition mechanism, is considering that we are going through what we call a coexistence phase. So this is like a weight where we have, with the mic is difficult, let's say we have the weight, the scale, you say scale, weight, we have the IPv4 traffic, which today is weighing more than IPv6, and then we are doing a coexistence of both protocols, and slowly the traffic will change from more IPv4 to more IPv6, and of course less IPv4. That's what we mean with transition and coexistence, okay? So we need to support, at least in the edge of the network, again, both edges, the service providers and the customer LANs, we need to support during some time, and nobody knows exactly how much time that means, because it will depend on how much it takes for everybody in the world to deploy IPv6. It will be a point probably where maybe 90% of the traffic is IPv6 already, and then some ISPs will say, hey, I don't want customers which demand IPv4 because they are actually costing me more money than the profit that they give to me, okay? That happens, for example, with all telephony systems. In my country, some of the ISPs providing all analog telephony systems, at a certain point, they talk to the customers, hey, I am not going to renew you the contract. Either you move to voice over IP, or sorry, I don't provide any more analog service. Because it's not worth, okay? So this is something that it may happen at some point with IPv4 as well. As I said, this is not the end of the, let's say, history, because we still will be able to provide, as I mentioned before, IPv4 as a service. But it's a different kind of service, and it has some advantages, but also some disadvantages. So we will look at that later. So, basically we define it in IETF 3 types of transition mechanisms. Let's go one by one. The first one is what we call dual stack. Dual stack is the same as what I mentioned just a minute ago as coexistence. So we have both IPv4 and IPv6 working at the same time in a given host or router, okay? So, how the applications, or sometimes the operating system, or the combination of both, will decide if using IPv4 or IPv6 if we have both? Well, that's depending on DNS. We have in DNS, everybody knows about DNS, right? Everybody knows what is an A record. An A record is the IPv4 address. And then we have a new record, which is the Quad A record, which basically means 4 times the size of the IPv4 address. 4 times the size of 32 bits is 128 bits, which is what we have with IPv6. And the operating system or the application, for example, a web browser, will contact the server, will query, for example, www.google.com, and then it will get, instead of an A record, it will get a Quad A record. What that means? Hey, you are connected to IPv6 and you have IPv6 stack, prefer IPv6. Okay, so it will try first IPv6, and only if the delay between IPv4 and IPv6 is too big, will fall back to IPv4. So if IPv6 is failing, in some circumstances, unfortunately not always, but most of the time, it will fall back to IPv4. Okay, so that's the way we change the balance. As more servers and clients are able to do IPv6, more and more traffic is IPv6 and less traffic is IPv4. Okay? When this fallback is not going to happen, there is a situation, and this is something that sometimes we do in IPv4 and we should not do in IPv6, is filtering ICMP. To discover if there are patent queue problems, the ICMPv6 need to be able to reach the end side, okay? So if you are filtering path NTU, what it will happen is that if the IPv6 path fails, the host will fail to fall back to IPv4, and that's a big problem. I am trying to teach some big content providers, like for example 1&1 in Europe, they have the load balancers improperly configured, and if your MTU is smaller than 1480, for example, you're using a tunnel or you have tunnels in your broadband access network, you never get that website, okay? Because it's not able to fall back. So this is something that a lot of people is doing wrong because they have the previous knowledge in IPv4 to filter ICMP, and that's it. So one of the things I like to say when I talk about IPv6 or when I do trainings on IPv6 is IPv6 is not more difficult than IPv4. Actually, it's easier, but the problem is that we have our mindset for IPv4, and if we follow everything the same as in IPv4, we will get it wrong. Okay? So please, when you do IPv6, don't look everything at the same way as we do with IPv4, and that's especially important for this thing, which is ICMP. We have the same problem filtering ICMP with IPv4, but most of the time is fixed already. Or for example, the big difference of providing, when we do the addressing plan of providing a single address in IPv4 versus providing a prefix in IPv6, okay? So those are things that work different. It's not related to transition, but I think it's worth to mention here. Okay, so everybody got clear maybe about what is dual stack? Let's see it in a picture. Let's suppose we have a dual stack host in the middle, okay? I think I have a pointer here. Let's see if it works. Yeah. So this is an a dual stack host. This is an IPv6 only host, and this is an IPv4 only host, okay? And I have this picture because I want to understand you some of the problems that we will find in the future. And we will describe it through the rest of the presentation. So, first thing to notice, when we talk about dual stack, it's not actually having two complete IP stacks, because TCP and UDP, most of have exactly the same code. So typically, when you have an IPv4 only stack, it takes today only, who knows how many kilobytes it takes a stack today? Usually no more than 30 kilobytes. So a stack is so well optimized today that it takes only 30 kilobytes. So having IPv4 and IPv6 that means twice, that means 60. Usually just 10, maybe 15% more, okay? So actually, from the point of view of the developer of the stack, it's not a dual stack, it's an hybrid stack, okay? So the stack has some common code, some IPv4 only code, and some IPv6 only code, okay? So that's the point. And let's suppose, and this is happening today already, that we have an IPv4 only host. Let's suppose we have a weather sensor in Alaska, and that sensor is working, and nobody's going to go there to the top of the mountain to change it. Maybe it's not Alaska, maybe here in the Everest, okay? Nobody's going to change it. And don't make sense. It's working, it has just an HTTP interface, and we have an IPv6 only cellular phone, which is happening already, okay? If we have in the middle something in the ISP network that make this translation, it will work, no problem. Especially for, let's say, simple protocols like HTTP. Very complex protocols, it may be slightly different, okay? But today we are going more and more to use more and more HTTP for everything, so that should not be a problem. And if we get things like VPNs and things like that working, that's sorted out, okay? So most of the time that will work perfectly, and we will see how we can reach this point. There is some interest, in addition to the lack of IPv4 addresses, there is some interest, especially in the cellular world, but I will say we can apply that also to the rest of the devices, even if they are not cellular, in terms of energy saving. If you have an IPv4 stack in a cellular phone, because you are using typically a NAT, you need to send what we call keep alive packets, typically every 30 seconds. So even if there is no real traffic, the cellular phone is going to say, hey, I am here, keep me the NAT ports open, and that again and again every 30 seconds, sometimes between 30 seconds and 2 minutes. It depends on the configuration of the network, the technologies, and so on. Okay? So that means processing power, it means battery life, and one of the things that the customer wants is a cellular phone that lasts longer. Okay? So that's against one of the principles of having a smaller cellular phone, more powerful with more battery life. So this is one more reason for the cellular phone providers, in addition to, even if the stack size difference is very small, to consider in the near future to go to IPv6 only. Okay, in addition again to the lack of IPv4 addresses. It's like the small drops that fill the glass, right? Everything counts until you say, hey, no more, I want an IPv6 only cellular phone, and that's going to happen. In fact, there are more and more cellular providers moving to IPv6 only in the access network for the cellular phones. Okay, we will see it later. Okay, everybody got this concept of dual stack clear? Any questions up to here? Okay, please again interrupt me at any point. Now, second type of transition mechanism is what we call tunnels. Everybody knows what is a tunnel. Everybody somehow is using a tunnel. When we set up VPNs, that's a tunnel. There are many ways to set up tunnels. We will go to describe in the next slides a few of those mechanisms to set up tunnels. Now, the simple one. Let's suppose we have an IPv4 only ISP, but we have two networks, two edges, that have already dual stack inside. And we want, through this IPv4 only ISP, we want to communicate end-to-end with IPv6. So the most simple way is setting up an IPv6 in IPv4 tunnel, which basically means we have the IPv6 header, which an IPv4 header before. So the IPv6 packet becomes the payload of the IPv4 one. Okay? What that means? Just one thing, and that's the reason it's important not to filter ICMP v6, at least not the message information. You can filter record reply, but not the rest of the things. So what that means is that because the IPv4 header takes 20 bytes, the MTU will be typically reduced by 20 bytes. So if you have a 1500 MTU, which is the default MTU in Ethernet, you will have only for the IPv6 transfers 1480. Okay? You should not need to configure that manually if ICMPv6 is not filtering. If in addition to that, you have some broadband broadband technology like PPP over Ethernet, it means some less bytes. So again, the need to not filter to avoid configuring them to manually in all the places of the network. Okay? Okay, there are. Oops, what's going on? Okay, there are other ways to encapsulate IPv6 in IPv4. The one I just described is this one. Oh, come on, this one. This is the most simple one, 6 in 4, IPv6 in IPv4, okay? Don't confuse, and I have seen documents from service providers and from vendors that confuse 16.4 with 6.4 with 6/4. They are different transition technologies. So if you see that in a document, make sure to get from the vendor that is providing that document if it's the real IPF technology, because it's incompatible. It will not work if in one side you configure one thing and the other side the other thing. I have been in that situation several times, okay? So, the most simple I just described it is, as I just said, 6/4, IPv6 in IPv4. So it's just using IPv6 as payload of an IPv4 packet. There is another very common mechanism for tunneling, which is GRE. I think it's protocol 47, okay? So GRE is very common in ISP networks configuring manual tunnels, because in this case of 6/4, there is not a control plane. So if the tunnel is broken, you only know that because the data is not reaching the other side, okay? Another important question I forgot in the previous slide. When you configure a tunnel, you are actually configuring two directions, okay? From A to B and from B to A. That's natural for tunnels, the same here for IPv6. So, with GRE, you have a control that allows you to know that the tunnel is broken even if you are not at that time transmitting data. So that's the advantage of GRE compared with 6/4. And then, because we have NAT boxes, it means that most of the time, unless the NAT box supports 6/4 or IPv6 GRE over IPv4, we need to support transporting IPv6 in UDP in IPv4. It's not as efficient as the others, but at least it traverses NAT boxes. One interesting comment here is many people still believe NAT means security. This is broken. Okay, NAT is not security. Usually, if you get security with NAT, it's because there is some kind of firewall also over there. The only way to get a secure network is a stateful firewall, okay? And we will see later, if you are able to make a hole, to punch a hole in a NAT box using UDP, it means it's not secure, okay? We will see later. Now, in IPF, we tried since the beginning to make it very simple, these transition web systems. And for that, we invented as many transition mechanisms as scenarios we can see. And that, which means looking for the best choice for every case, is a nice goal, but it means it makes the life more complex to you, because you need to read 500 documents from IPF to understand which one to choose. Okay, so it's a nice goal, but actually it has been a bad thing for the IPv6 deployment. It's true that we learned it through the experience. So we invented some transition mechanism and we realized, hey, wow, this is nice, but we can do it better. Let's do it better, and so on. Okay? So, or we discovered that some of the mechanisms have some, let's say, pains that we don't want to go through. So, I am not going to talk about all of them, but I just mentioned here some of them, and I am going to go through a few of them, not all. So the first one is the one I described before, okay? It's the general concept of IPv6 and IPv4, and then we have, I think we have a bigger picture, then we have from this host to this router, an IPv6 in IPv4 tunnel, and also tunneling the other way around, okay? So we are able to send and receive data. This could be done also from host to host, router to router, never mind. Okay, so we have here all the possible combinations. Now, let's suppose you have an access technology that don't allow you to do native IPv6, so you need to use this kind of tunnel. Let's suppose you have 500 customers. This kind of tunnel means manually configuring each of those 500 tunnels for your 500 customers. Well, it's possible. You can somehow automate it, but if you have 10,000 customers or 100,000 customers, do you really think this is the best way? Definitely not. This is still a good option, either this or using GRE, if your upstream provider don't have still IPv6 native support, maybe in the POP that you are connecting to, and meanwhile they deploy the IPv6 native support, you can use this. That's not bad, okay? Maybe you need to do several tunnels to have backups, or to different POPs, or to different upstream providers, but we are talking about maybe 3, 4, 5, 10 tunnels. That's okay, okay? It's not ideal. If you can push your upstream provider to deploy native IPv6, that's where you should go, and you should say them, hey, if you don't provide that in the next 3 months, I will switch to another transit provider, clearly. Okay, that's market, competition. But if you have no other choice, that's a possibility. Sometimes it happens, your access provider, your upstream provider don't have IPv6 yet, but the next after him provide the service. So then maybe you can use this kind of tunneling to jump over your actual upstream provider. Okay? Sometimes it happens in some countries because the laws, the regulations don't allow to have transit providers which are not the national ones, and I have seen that situation. But this is a way to sort out the problem. So, to avoid this manual configuration, we decided to make what we call a tunnel broker. A tunnel broker, and there is a very nice service, I believe today only one company is providing that, which is Hurricane Electric, tunnelbroker.net. Basically it means, instead of having a manual configuration in both sides, you have a manual configuration only in the local site, but the remote router is automatically configured when you register in the web page for the tunnel. Okay? And it's free, and that's it. And that's good for end users that still cannot get IPv6 from their own access providers. So that's the basic idea of the tunnel broker. We went through the process to find a mechanism that standardizes this, and I believe that the only standard protocol for that is what we call TSP, Tunneling Setup Protocol, which is basically an XML interface, but it's not really longer in use. Okay? So, for example, in the case of Hurricane Electric, tunnelbroker.net, basically what happens is that you can get the configuration for configuring the tunnel when you go into the web page of tunnelbroker.net. It tells you what you have, a Cisco, macOS, Windows, you select whatever you have, and then you get the configuration for your tunnel, okay? You can just put that in a script, and that's it. Now, we tried also to make what we call automatic tunnels. You should not use this protocol anymore, but I think it's important that you have an idea about what it means. 624 is a way to do tunnels without any manual configuration. You just tell your router, sometimes it comes enabled by default, hey, use 624. Remember what I said at the beginning. 6-in-4, 6-to-4, 6-over-4 is not the same. Many people confuse them. It's not the same. It's true that 6-to-4 also uses the same encapsulation, so 6-in-4, but it's not a 6-in-4 tunnel. It's the same way to encapsulate packets, so it's having an IPv4 header in front of the IPv6 packet, okay? So what means 6-to-4? 6-to-4 means if you have an edge network that has a 6-to-4 router, a router that supports 6-to-4, And this is supported by all the vendors, even all the operating systems, Windows, Macintosh, Cisco, everybody supporting 64, even very, very cheap routers for the home support 64, or I remember Apple Express was enabled by default, and so on. So if you have this access network, and the router is getting a public IPv4 address, and there is another network in the same situation, and we have an IPv4 only internet or service provider, or a set of service providers that only support IPv4, because this router is using 64, it will create a special IPv6 address. This IPv6 address is created with a special IPv6 prefix, which is 2002. 2002 is how many bits? Hexadecimal, IPv6, the first part. How many bits? 16. Now, remember that we have a public IPv4 address. How many bits is an IPv4 address? 32. So we have 16 plus 32. How many bits? 48. What we have? We have a /48 for this network. So we have the IPv6 prefix followed by the hexadecimal of the IPv4 address. So we have a unique IPv6 prefix, the /48, and it's unique because it depends on each IPv4 public address. So nobody will have in the world the same prefix. So that means these two networks can talk peer-to-peer using IPv6, encapsulated in IPv4, automatically, no configuration at all. Just say, if it's not enabled by default, hey host, enable IPv6, 624, or router, enable IP624, that's it. Okay? So this is very nice, and for peer-to-peer it works very well. I heard about some applications like BitTorrent and so on that use this as much as they can instead of using IPv4. It's more efficient. Okay, so if you see the sources of the torrents, you will see a lot of this. Of course, only works, again, if you have here a public IPv4 address. Okay? Now, what happens with this protocol? If you want to talk using 624, which, for example, Google or Facebook or whatever, because they don't have a 624 enabled, you need somebody in the middle that translates 624 to native IPv6. That's what we call the 624 relay. We have a relay here and relay here. At some point, there were some number of relays in the world, but it was growing and growing, the number of people using 624, and nobody was offering more and more relays, so the capacity was not enough. So this turned out into a big problem because you are getting a lot of packet loss, delays, and so on. The ideal situation would have been that the ISPs that cannot deploy native IPv6, they deploy their own 624 relays. That didn't happen. Okay? And by the way, the 624 relays are discovered automatically by a protocol which now has been deprecated by IETF, which is Anycast. 624 relay Anycast. So it means that you are trying to find automatically the closer 624 relay to you. So again, if the service providers have deployed relays, the big service providers or the ISPs or both of them, that would have been a good solution, but didn't happen. So you should not use 624 today to provide service to customers. They will use it maybe automatically for peer-to-peer communication, that's fine, if you don't have native IPv6 access. Here are a few details I already mentioned. For example, the prefix 2002::16, and the document that describes the Anycast, which was the address 192.88.99.1. Well, it was the full 24 for that address. And again, this only works if you have a public IPv4 address. But typically what happens is that you have a public IPv4 address, or maybe even not a public, a private one, and you have an NAT box. And here is what I mentioned before, that even having a NAT box means it's not secure, because we can punch holes to make this protocol work. Let me explain how this protocol started in IETF. There is a person that at that time was working, it's a French guy, Christian Utema, that was working for Microsoft. And he sent a proposal to IETF called Shipworm. And of course, IETF, many people didn't read the document, because a document with a title of Shipworm is not a nice title for an IETF standard. So he realized that instead of using Shipworm, because in Europe, many of the languages that we speak are born from Latin, and we still study Latin, he knew that in Latin, Shipworm is called Teredo Navalis. So he used only the first word and said, okay, the next, IETF don't like Shipworm, the next release, I will change the name. And nobody, most of the people, probably 50% of the people in the IETF, which are English speakers and they don't learn Latin, didn't realize that it was the same, but it's a different language. And then it was accepted. Okay? So it was not just because the content of the document, which you may like or not, but it was just the name that people at first sight didn't like it. So that's the reason it's called now Teredo Navalis. Teredo Navalis is the worm that makes the holes in the wood of the ships. Okay? So it's a worm. And it's trying to say that what it's doing is making holes in your NAT box. So again, don't believe NAT means security. Okay? So how it works? It's very similar to 624. You have a NAT box, don't need to support IPv6. The IPv6 support is in the host. And today all the operating systems, well today, since 2003 more or less, all the operating systems support IPv6. And we have our counterpart having the same situation. So what you need is a Teredo server, which Microsoft has a lot in his network because it's still offering this service. And this Teredo service has a very peculiar thing. It has two consecutive IPv4 public addresses. So once one of these hosts say, I want to use Teredo because I don't have native IPv6 in my network, it sends a packet to the Teredo server. The Teredo server is discovered using IPv6 Anycast. Instead of IPv4 Anycast, IPv6 Anycast. Okay? And then, the Teredo relay is covered by Anycast. In this case, I think it has fixed addresses, which probably are also IPv4 Anycast. I don't remember right now the exact data. But the point is that this host here sent a packet, which we call a bubble in the standard, to the Teredo server. And the Teredo server used the two consecutive addresses to make a trick to guess which is the best way to make a hole in the NAT box. So if you are a hacker and you have two IPv4 consecutive addresses, you can use the same procedure to make holes in any host that you want to attack. Okay? It's not so easy, but it's possible to do that. So again, not equal to security. Make sure to understand that. So once this host gets the response from the Teredo server, as part of the response, he's getting his IPv6 address. In this case, it's a /64. Okay? And what that means is that the host in the LAN can talk IPv6, but also the remote host using Teredo can speak peer-to-peer, encapsulating IPv6 in UDP IPv4. Okay? And again, same situation as in IPv4. By using Anycast, in this case is IPv6 Anycast, they discover that the red relays to talk to Google, Facebook, etc., etc. And that's the bad part. This works very well if they talk to IPv6 services offered by Microsoft because they are supporting it, but not by third parties. Okay, so again, this is not something you need to deploy. If you want to support it, you could deploy the relays in your networks, the same as I mentioned before, you could support it by deploying 624 relays in your network, but really probably don't make any sense unless you really cannot deploy IPv6 in other ways. Okay? So it's not the best way, but it's an option. Let me skip this, what I just explained. Okay. I mentioned already the history of why we have developed so many transition mechanisms. And at the last stage, or almost the last stage, when IPv6 was already being deployed, let's say, with a good effort globally, we were still trying to solve the problem of which is the best solution, and especially we were looking to cellular networks for finding the best way. So we set up a new working group. I was part of that effort, which we call it Softwires. And most of the latest transition mechanisms that have been developed have been done in this working group. And there is still some ongoing work. What we were looking here was a transition mechanism that provides, I'm not going to read them, but provide all these kind of features. Okay? And then one of the candidates was TSP, I mentioned before, Tunneling Set Protocol. Another candidate was, so I wrote a new protocol, I call it ATS6. I don't remember what it was. It was like automatic tunneling setup, IPv6 or something like that. And then Cisco come to the table and they said, hey, we don't need anything new. We have something already. We just need to tweak it a little bit. And that was L2TP. L2TP has the advantage that many providers already use L2TP in their networks. So instead of inventing a completely new protocol that needs to be deployed everywhere, we can just amend that protocol, adapt it to transport IPv6. And in fact, the idea was not just transporting IPv6, it was looking at the next stage. So we wanted to be able to transport IPv6 on top of the Softwires header. This is the modification we did, the Softwires header on top of IPv4. We want to be able to do that to traverse NATs also on top of UDP. But we want to consider also the reverse scenario, when we have IPv6 only networks and we want to traverse them with IPv4. Okay, so I mentioned before the concept of IPv4 as a service. Okay, that will be one way. But we wanted also to be able to do this IPv6 in IPv6 and IPv4 in IPv4. Why? Because, for example, you have an IPv4 on IPv6 unicast network and you want to support multicast traffic. So this is the way. You have IPv6 multicast and IPv6 unicast, and the same for IPv4. That was the idea. So this protocol, I'm not going to describe it because basically, if you know L2TP is the same, it has a data channel, a control channel, and that's it about. Okay? So the scenario of using this Softwires mechanism is basically you have a router that needs to support L2TP or Softwires, and we call it Softwires initiator. Okay? And then you have the Softwires concentrator, which is basically the L2TP router in the ISP network. Okay? The L2TP concentrator. And that's basically it. It offers the advantage of having AAA, so you can authenticate the tunnels and so on, and it's automated, blah, blah, blah. So that was the idea. We worked on that using both L2TP version 2 and version 3. We expected that L2TP version 3 will get a major deployment. Actually, it didn't happen. happen. So most of the deployments of L2TP today are already still using the old version, which is version 2. And what happens basically is that even if we expected this to take up, it didn't happen. So there are very few deployments using subwires in the world, but we have made new transition mechanisms that we will describe next, which are using subwires. So it's the base for other transition protocols. Okay? Basically, the way we are transmitting L2TP, we are using the same for other transition mechanisms. Okay. I already talked about 624. Maybe I need to change the order of these slides. I never remember to do that. There is an alternative to 624 that got some good deployment, especially in Europe, which is called 6RD, 6 Rapid Deployment. 6RD was an idea about a French ISP that basically they used their own Linux set-top box. They designed it, and they said, we cannot do native IPv6 because our network is not really ours, it's France Telecom network. So we are over the France Telecom network. So the only way they had was using 624, but they didn't like the idea of having any fast relays, and they wanted to have their own 624 gateways. Okay, so they changed a little bit the 624 protocol into 6RD, and then they convinced a Cisco guy that was living in France at that time. I think he's still living there, to support that protocol. And they tried to convince a lot of people in IETF, including myself, and we said, no, we don't want any more new transition mechanisms. But when Mark Townsley, which is that Cisco guy I mentioned, got IPv6 at home, said, how come a small ISP is giving me IPv6 and Cisco has not been able to give me a solution? So he decided to be co-author of the document, and they made it standard. So how it works? It works under the same idea 624, same encapsulation, which is 6 in 4, but instead of using the 2002 prefix, is using the prefix that the ISP got from RIPE in Europe, APNIC here, and so on. Okay? So what that means is that you don't need relays because it's your prefix, you know the traffic is coming to your network. Okay? Disadvantage, if you get from APNIC as last 32 and you put there the complete IPv4 address, you only can give to the customer as last 64, which is broken in IPv6. Typically in IPv6, my recommendation is give the customer as last 48. Some people go for as last 56. There is a document, a recent document from RIPE, I think it's RIPE 690, that describes why it's good to go for a slash 48. Okay? This can be sorted out. How? Getting a bigger prefix than slash 32. In RIPE, in fact, we changed it. I am one of the co-authors together with Mark Townsley. We changed the RIPE policy, and by default, you can get a slash 29. And instead of using the complete IPv4 address, you use only part of it because you know how is your network and how is the routing, so you can use only 16 bits of the IPv4 address of the customer, right? So at the end, you can get here any number of slash 64s. So perfectly, you can get again a slash 48 for your customer, okay, or something in the middle. Okay. So this is a good protocol. There is good support in CPEs, but it has one disadvantage. You need public IPv4 addresses. You could do it with private, but it's not nice. Okay? And probably you are coming to the point where you don't have any more public addresses. So this is probably not the best solution today for some of you. For some others, maybe. Okay, but not for everyone it will work or will scale in the long term. Now, the last set of transition mechanisms is what we call translation. When we started making the first translation mechanism, it was in fact designed to translate just HTTP packets. So the idea was, okay, if we have an old web server and I cannot do IPv6 to that web server, let's have a kind of translator or proxy in front of it. So customers that already have in their browsers IPv6 support, let's allow them to connect with IPv6. That worked very well. That first translation mechanism was called NAT-PT, which stands for NAT but protocol. So translate not just the addresses but also the protocol between V4 and V6. Okay? However, we are engineers, we wanted to use NAT-PT for all kind of things, not just HTTP, and the problem that means you need to start using what we call ALGs, application layer gateways. And as soon as you start having new application layer gateways for every functionality like DNS, FTP, or whatever, the performance of that box will go down, down, and down because it's going to process by software many kind of protocols. So it doesn't scale. And we decided the idea to get rid of, so to deprecate that protocol and say, hey, we don't need translation mechanisms. And yes, it's true, we don't need translation mechanisms if we started to deploy IPv6 earlier. But the problem is that we were so slow that we ran out of IPv4 before deploying IPv6, so we have a problem. And that means we needed to go back to design some new translation mechanism. Okay, so that's the reason we now, despite in my trainings a few years ago I was saying never use translation. Now I need to tell you, please, I was wrong. You have no other way than using translation. Okay? So, that's the description I just made about the NAT-PT. Okay? And if you remember the slide that I had when I talked about the dual stack, that was a translator, basically. It's something in the ISP having dual stack, IPv4 only in one side, IPv6 only on the other side, and a translator in the middle. Okay? That's a translator. Now, let's go step by step to the different options. The first option, this is the AGL. It's not 666, it's 444, but this is the AGL. Basically, this is what we call carrier grade NAT. You have probably different terminology like LSN, which stands for large scale NAT, or CGNAT, carrier grade NAT again, and so on. Technically, in the RFC, it's called AFTR, Address Family Transition Router. This is one of the words of this working group I mentioned before, which is SOCWISE. Okay? So the idea here is not to deploy IPv6. Many people confuse carrier grade NAT with IPv6 deployment. You can do carrier grade NAT and not do IPv6 deployment. Carrier grade NAT is a very nice solution for vendors to sell you new boxes, very expensive boxes. If you can avoid that, please do it, avoid it. It's very expensive, it's difficult to maintain, it costs a ton in logging, depending on the regulation in your country. It creates a lot of problems. Okay? For example, if you have customers using PlayStation, as soon as Sony discovered that you are using some IPv4 addresses or prefixes for carrier grade NAT, they block those addresses, go into a blacklist, and never, ever will go again to a whitelist. So it means you need to keep replacing the IP addresses to your gamers because those addresses will not reach Sony PlayStation network again. Okay? The interesting thing is that Sony as I know, is still not doing IPv6, so this is contradictory, but that's another history. Okay, so they either say, hey, if you want to play with Sony network, do IPv6, but they don't support it, at least not in Europe, as I am aware. I am not a gamer, but that's the news I have. Okay, so what is NAT44? It's combining two NAT boxes. It's one NAT that we have today already in every network of our phones, at the CPEs, and then another big box, a big NAT box in the carrier. It's true that this has been used in the cellular world for a long time, but the difference is that in the cellular world, the NAT box is not in the cellular, it's only in the carrier. So you have only one level of NAT. Here you have two levels of NAT, so this is the picture. So, assuming you have a network that don't support IPv6, instead of having here the public address, which is the most common way today, you will get a private address. It may be the same for all customers. And then you have the public address moved here, and you have one first level of NAT44 and the second level of NAT44 in the AFTR, which is the carrier grade NAT box. Okay? And yes, it's true. If you replace this box to one that has IPv6 support, the IPv6 traffic will go straight without going through the carrier grade NAT box, but the IPv4 traffic needs to go to the carrier grade NAT box. So this is a way, but my recommendation is don't do this. It's more costly than what it seems, looking at the cost of the boxes. Even the boxes are already expensive. I think there are better choices, and we will go through them in the next slides. Those are some of the things that carrier grade NAT breaks. There are solutions to some of those things. There are vendors that already have the solutions built in, but most of them are ALGs, application layer gateways, so it means you have lower performance when you are using them. Okay? So it's the same history as I mentioned before for NAT PT. Now, we don't have IPv4 anymore. I think everybody's know that. So, why we consider deploying IPv6 only to customers? And that's what we do with basically the next set of transition mechanisms. The first one is what we call DS-Lite, dual stack Lite. Basically, DS-Lite is a combination of a NAT and tunneling. And the way we do that is by converting the NAT box of the home user into a bridge, which we call DS-Lite basic bridging broadband. We call it abbreviated B4. Okay? And then we have the carrier grade NAT to do the NAT functionality at the ISP. So this is somehow a better solution than NAT444 or simply carrier grade NAT, because as I just explained it in the previous slide, in the carrier grade NAT solution, you not necessarily are deploying IPv6. Instead, here you are forced to deploy IPv6. How it works? We need to have a CPE that supports this protocol. We call it DS-Lite support. Instead of having an IPv4 access, we have an IPv6 only access. So these links will turn into only IPv6. But the B4 is doing an IPv4 in IPv6 tunneling to provide IPv4 to the LANs of the customers. Okay? So it's the reverse that we were doing when we talked about the first tunneling, which was IPv6 and IPv4. Now we do IPv4 and IPv6. Okay? Disadvantage, we have the big, expensive, and bad able box. Okay? It's true that this is a better solution because if we compare it with NAT444, here we have only one level of NAT. So we need to move the NAT from here to here instead of having two NAT boxes. Okay? So we break less things, still break things. Having a carrier NAT still means Sony PlayStation will ban you with addresses, for example. Okay? Questions up here? I think we have 30 minutes to go, or a little bit less, 20 minutes. No questions? Okay. Next thing, next protocol. If you decide to go to the slide, I will strongly suggest you to go to this version of the slide. You will easily understand why. Lightweight 4/6 is basically the same as the slide. Let's go to the picture already. I think it's easier to see here. But instead of having the NAT box here, we move again the NAT box to the CPU. So we do the same as with the slide, but the NAT functionality goes back to the CPU. What that means, the cost and the overhead of the lightweight carrier NAT box in the ISP is lower. And it means it can scale better. Still you are sharing addresses. Okay? So sharing addresses still means Sony PlayStation and maybe other service providers will ban you sooner or later. Okay? But at least this box becomes less heavier and cheaper. One thing I didn't mention, and it's common for all the usage, all the versions of carrier NAT, is to share IPv4 addresses among different customers. How we do? Who has an idea? How can I share IPv4 address among all the people here? What we do? We give every possible user, instead of the 65,000 ports, only, let's say, 1,000. Only 1,000 ports for each one. What that means, some protocols like Ajax that make usage of more and more and more ports every time may fail. And we will see some examples later. Okay? And of course, from the perspective of the user, maybe he's not going to notice it immediately, but again, this is not providing an internet service, it's providing a subset of internet. So it's not just an IP address, it's providing a part of an IPv4 address. What that means basically is if we all are neighbors of the same building and we are using the same IPv4 address, and somebody here downloads file downloaders web servers, and at the next minute another user of the same building is downloading a file, he will get the typical message, you need to wait 5 minutes because you just did. Oh no, it was not me, it was my neighbor. You see the point? Or if your neighbor is doing some internet, how you know who was? And that's a problem for authorities, for police, for law enforcement authorities. For example, Europol is working together with the European Commission to get rid of that. Because that's a big problem. There have been crimes that have not been able to be solved because this. Because you cannot say, okay, if 60 people is sharing the same address, and I know it was a threat or some alert of, or some, how to say, something to prove that that person who is, has the law the right to go into the privacy of 60 people to accuse one? That's a big problem. Okay? You may be forced by your regulator to log more data, like port numbers and so on. But that takes 2 or 3 years and then 2 or 3 years to implement in your network. And implementing IPv6 takes probably less than that. That's the situation right now happening in Europe. In most of the cases, the ISPs will get a warning from the authorities, we are going to change the law, you need to adapt your logging system to this. I don't need that boxes and I don't need so much logging. Okay, next big thing we invented, NAT64. NAT64, I think the word is telling you about that. It's making a NAT, a translator between IPv6 and IPv4. So that's meant basically for those services, for example, websites that are IPv4 only, which today there is no real reason to keep a website which is IPv4 only, but we know people is slow to take up to do that. Okay, so you provide IPv6 only service to your customers. So with NAT64, we do this translation automatically, so it should work in theory. To be able to work, it uses a help, which is what we call DNS64, which means if you have a website which is IPv4 only, it will have an A record only, right? So what DNS64 is going to do is to lie to the browser and tell the browser, hey, this has only a quadratic record. So you send the traffic through the NAT64 box, because the NAT64 box is going to translate from this quadratic record to the path to go to the IPv4 A record, more or less. That's the path. So I am going to describe the idea of NAT64. First, if you have here IPv4 only, that works. Okay? You need to have IPv6. If you have IPv6 browser to IPv6 server, okay. I am wrong with the time. I see the people leaving. What time is the lunch? It's at 13, right? So we have still 15 minutes. I was looking, some people is leaving, maybe I am wrong with the time. Okay, so you have plain IPv6 transport if both sides have IPv6. Now, if I have an IPv6 browser, but I need to go to an IPv4 server, I can have a functionality in the browser or in the operating system which is called the Quad A record, Quad A or IPv6 record synthesis. Okay? Making up, it can be done as already, especially in the server phones. We can make this record from an A record. So when we get the Quad A record, because it's lying to us telling that it has IPv6, we will route it through the NAT64 box that will have the public IPv4 addresses and translate to IPv4. Okay. What is the difference between carrier NAT and a NAT64 box? Many people believe it's the same, but the difference is that in carrier NAT, you are allocating a number of ports for every user. In NAT64, you have as many IPv4 addresses as you want, and each address has 65,000 ports, and you allocate them dynamically as soon as many requests come from users. So there is not a limit of ports per user. You see the difference? So it scales much better because you need to have less addresses and you support more customers. Depending on what is the workload of the different customers, some of them will use at some point 1,000 ports or only 500 or 20,000. You don't care. It's dynamic. Okay? So that's the difference. The cost will be lower and the scale will go high and high as much more IPv6 traffic is in your network. Okay? So that's the big difference. And it's much simple to deploy. It's true that if you go to the first option, and you don't need to replace the CPE here, as well as DSLi, Lightwave 4/6, you need to replace or update the CPE. Okay? So that's the difference between one and the others. Now, what happens with NAT64? Why it breaks things? Because it's based on DNS. And we know that unfortunately, some web developers or some application developers still use all DNS resolution libraries, or even worse, literal addresses. So 8.8.8.8 in your browser. That will not go through NAT64 because there is no DNS resolution there. You see why? Everybody got that? So NAT64, it would be fantastic if everybody makes software the right way. But this is not really. So we developed one more transition mechanism, which in my opinion is the best one, and the one that today has more deployment in the world in terms of number of users, because it's the transition mechanism that has been used by more cellular providers, and this is called 464. Look, things like Skype, Spotify, and many others were broken with NAT64. It's true that this is a bit old, I don't remember the date, it was a few years ago, and now maybe new releases of Skype or other applications have that don't really take this seriously and don't use names, they still use literals. Okay, so still you have the chances of having a deployment in your network of NAT64 and a lot of complaints from customers that cannot access certain sites. Okay, so NAT64, don't use it longer. If you want to use NAT64, basically is NAT64 and something else. And what's something else? Let's see it here. NAT64 is doing the 6-to-4 translation. What if at the CPE we do an 4-to-6 translation? 4-to-6 and then 6-to-4. We translate twice. If we translate twice and we don't depend anymore on DNS, we don't break anything. Okay? Because we don't need to look into the DNS. So we are lying end to end, making the translation one side and the other. So end to end, it will look like nothing changed. Okay? Of course, for that you need again the CPE to support the CLAT. The code for CLAT is like this size, it's 1 page. It's open source, it's available there, it's already many operating systems like Android, so it's available in many places. Okay, we will talk about that later more this afternoon when we talk about the cellular deployment. But it's really simple. I usually bring a small router, a $10 router that has OpenWRT. You know what is OpenWRT? You can flash almost every router in the world with OpenWRT, and it has support for this. So you don't need to have to a certain point support from the vendor if you have your team doing that. Okay, you need to have some knowledge of Linux and so on. That is big trials totaling about 10,000 customers with this, with open source routers. Okay, and I am talking about $10 routers, which have dual radio, 5 gigabit ports, and so on. So it's fantastic. I will bring it later after lunch so you can see. This is a very small box, but it's fantastic. Okay. PLAT is the name for the provider translator, while CLAT is the customer translator, is the abbreviation. Okay? How it works? Let's see. A server phone or a CPE, never mind, it's the same. And we have the PLAT, which is basically the NAT64, nothing else, nothing different. NAT64, by the way, there is a very nice open source version of NAT64. Joule works in many operating systems, it scales fantastically, so you can use that instead of buying boxes from vendors. You can have big servers, a bunch of them, so you have very high redundancy. You spend, I don't know, $4,000, $5,000 in 4 or 5 servers, and you do service for your customers. Okay, so that's easy. For DNS64, most of the DNS software like Bind, Node, etc., they support DNS64, so that's also sorted out. You don't need to buy anything. So the DNS64 functionality, and then either the server phone itself or the CPE has the CLAT daemon. It's basically a Linux daemon. Okay. So what happens is that if there is IPv6 traffic, it will go through a stripe. Of course, translation is all. But if there is what happens is that this translator is stateless from 4 to 6. So it goes as IPv6 through the IPv6 only access network of the ISP. Again, the important thing here is you don't need to have any more IPv4 in your access network. It's only IPv6. The PLAT, it gets translated again from 6 to 4 to reach the web server, which is IPv4 only. Okay? So simple. No overload of the devices in the ISP network, no overload of the NAT box, or the primary NAT box. And you will see, as soon as more and more of your customers and the services they access have IPv6 support, that the load of your NAT64 boxes goes down, 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 down. And then you can use those Linux boxes for something else if you want. Okay? So that's basically Linux. I think we can go on for that time. If necessary, I don't finish the presentation. We'll restart from where we finished this afternoon. These are the 3 possible scenarios of usage, and this is automated. You don't need to configure anything. Depending on what applications are here. First case, you have an IPv6 application going to an IPv6 server, straight. No translation at all. Is that clear, right? Now, second case, you have an application that is using DNS. So you do is lying to the application to fake the A record into a quad A record. And the last case, that traffic that is using literals get translated twice. Okay? How that's done? IPv6 basically is doing nothing. Actually, the CLAT is not called because it's IPv6 routing inside the box. Okay? When it's detecting DNS, does nothing. And only when detects literals or all DNS it's translation that. Okay? And then it gets translated again in the ASP network. That's how it works. If you want to see that, which an example of step by step in the addresses, I am not going to go through. You have the slide uploaded in the website. Look at that, and if you have questions, we can see that later. But it's quite simple, quite straight. You will get it very, very quickly. Okay? I got that picture from, I think it's a Google document from Dan Brown. And basically, this shows how make this deployment very simple, because this is the handset. Okay, so you have the CLAT diagram, and then you have the wireless, which is IPv6 only, and then you have in the cell providers the PLAT, the NAT64. You want to reach. Now, how is the availability of NAT64 and all the things that you need? Well, I mentioned already. You have NAT64 supported from many vendors. Almost every box that you have, they are kind of virtual boxes or virtual machines, but you need less boxes, okay, and less costly probably. You have the CLAT supported in many operating systems and also open source like Joule, OpenWRT, and so on. And then you have here. You have the DNS supported by most of the DNS open source and also commercial DNS. For example, IPAM boxes like Bluecode or Infoblox and many others that provide DNS, DHCPv6, IPAM for IPv6 and for IPv4. Something really universal because it's quite simple to deploy, to develop. Sorry. I am sure this number is not updated. I probably made this slide a couple of years ago, but at that time, T-Mobile has already 68 million of users is probably 10 times more than the number of users of all the other transition mechanisms together. And this is only one example, because now there are 4 big providers in US, America. I cannot say names, but they will come up like in a matter of weeks or months. In a single country, have 12 million of users that are going to use in the cellular network 464X LAT. We went already through all the testing, and it's just a matter of marketing decision. Is using also 464X LAT, and there are many other deployments using 464X LAT. Okay, so again, this is the point. Very easy to understand for the cellular network. Is the same for non-cellular networks. We will go through all that this afternoon. I'm using just 2 new transition mechanisms. I will start this afternoon with them. It's okay because the second session probably was shorter because part of the things I will talk will be again remembering about 464X and so on. So we need to repeat that. So we are right on time after lunch. And just to finish, questions up to now? Or if you have questions, we can start with that also after lunch. No questions? We will have an exam later. You get an exam, you go to the coffee. Here, if you want one of them, just come here because I need to take note of your email and your company and so on to register it. And I will bring 6 more after lunch, okay? So that's it for the moment.